Welcome back to part 2 of lesson number 5. We're going to look at natural logarithms today. Alright, so natural logarithms, these are logarithms that have the base of e. So an example would be if I had log e15, the base, remember, is e. So that's the subscript that's attached to your log. So e is an irrational number, so if we think of other numbers like pi, for example, then we can find the e function in our calculator, the e button in our calculator, and it's an actual number, and it's 2.718 if I were to round it to 3 decimal places. And so on a graphing calculator, we can evaluate log e15, and we can write it as ln 15, or natural logarithm of 15. So this can be evaluated using our ln key, ln. Alright, so if I were to use the calculator, ln 15, I get 2.708. Alright, so with this example, number 7, all we need to do is evaluate this using our calculators. So if I were to evaluate the natural logarithm of 5, I would just type in ln 5, and I would get 1.6. Remember that log with base e of 5 is the same thing as ln 5, so we know that that's going to be 1.6. And if I have the ln of e, or the log e of e, this is just equal to 1. And we can prove that using the calculator as well. That is equal to 1. Alright, so let's look at, well, this part, I guess you could do it, but all you're going to see is if you were to type this function into your graphing calculator and graph it, and if you look for all the values of x, so the first one at 10, you're going to find that that falls at 2.5937. So the question is asking us to find out what the y value would be at each of these values of x, and to use 4 decimal places to give our answer. Next, I had to be at 2.7048, and if you can see this, we're actually, the number is getting a little larger as we go up, but not by much. And so this is an indication that our value of e, so the estimate for e is going to be close to, when x is a million, 2.7183, and in our graphing calculator, where we use the e key on our calculator, we found that it was equal to 2.718. And then if we were to continue with our decimal places, it would be 281,828. Alright, so let's look how we actually use these natural logarithms and where they come in useful. Before we actually do that, though, let's look at another concept of changing bases. So if I were to evaluate log 525 using exponential form, this is what we were doing yesterday. And so this is when we set this equal to v, and then we converted this into exponential form. So remember that v becomes my exponent, 5 to v, and my argument becomes my value of x. So 25 is equal to 5 to the power of v. If I were to express 5 or 25 with the base of 5, I could express that as 5 squared is equal to 5v, and I would get an answer of v is equal to 2. Now another thing we could do is evaluate log 25 divided by log 5 and ln 25 by ln 5 using a graphing calculator. Now when I use the log function in my calculator, it's just the one right underneath of my x squared button, so right here, and it'll say log. This gives me log base 10. Alright, so we're using a common log in order to come up with an answer. So that is equal to 2, and if I were to use my natural log divided by 5, I'm going to get the same answer, 2. Okay, so they're the same. Now, how would I evaluate log 3 of 243 by converting to exponential form? Well, same thing we did up here. I'm going to have to set this equal to v. And exponential form, I would be left with 3 to the v. 243 as a base of 3 is 3 to the power of 5, and that is equal to 3 to the power of v. We drop our bases and we're left with v is equal to 5. Alright, so if I were to evaluate log 3 of 243, that is equal to 5. Now if I were to evaluate this in the calculator, I'm going to get the same answer. Both of these are going to equal 5. Okay, so remember log e is the same thing as natural logarithm, as ln. Alright, so same thing, you're going to get the same answer. So in the first page of this lesson we learned that log 2 of 8 was equal to 3. Now what we want to do is write log 2 of 8 in a form which can be evaluated using a calculator and verify the answer. So if we were to put this into a calculator, log 2 of 8 is equal to 3, we would have to convert it into common bases. So the common base here would be base 10, just like we did up here. If we compare what we did in each of these examples, I can make this log 8 divided by log 2, and that would give me an answer of 3. And you can verify that this question in your calculator and you're going to get the same thing. So write log 264 in a form which can be evaluated using a calculator. Exact same way, log 64 divided by log 2, and if we were to put this in our calculator, log 64 divided by log 2, we're going to get an answer of 6. Now, this is called the change of base identity, and it follows this principle. If I have log b of c, that's going to be equal to log a of c divided by log a of b, where b is equal to my arguments, so the base b is equal to my argument out of my denominator, and log c is going to be the argument of my numerator. And then I choose a common log, and so usually if you're using your calculator, we're going to just use log of 10. Alright, so evaluate log 4 of 1024 using the calculator. Well, if you're going to type that in, we're going to type it in as log 1024 divided by log 4. And if you were to type this in, you're going to get an answer of 5. Now, if we have something that looks a little trickier, what if I have log 2 of 1024 divided by log 2 of 4? Well, it may look complicated, but it's not as bad as it may seem. So first of all, let's think about what we're being asked to do and how we would actually calculate something like this. So if I have log 2 of 1024, this is something that I would have to break down into my change of base identity, and I would have to express this as log 1024, so log a of c divided by log a of b. Alright, and so I'd have to divide these two terms, and then I would have to do the same thing on the bottom. And so using my change of base identity, this is going to become log 4 divided by log 2. And if you were to calculate this, you're going to find that you're going to get, this is going to be 10 divided by this answer, which is 2, and this is just going to equal 5. Okay, so let's look at some that are a little trickier. You should be able to input both of these into your calculator, but let's look at this one at 3 log 7 512. So the first thing I want to do is put this in our calculator in a form that is useful. So if I have 3 times log 7 512, I'm going to put it into a form using my change of base identity where we have a common base. So we're going to use base 10 again. So it says 3 log 7, this is going to become 3 log 10 512 divided by log 10 of 7. Now, if we were to calculate this, we're going to end up with 3 times log 512 divided by log 7. And we're getting an answer of 9.62 if I round to the nearest hundredth. Alright, so all it really is a matter of finding the common base, and if you're using your calculator, your common base is just going to be 10. And then remembering that this stays on top and this one goes on the bottom. All right, so convert the following logarithms to the base indicated. So I want to convert log 6 of 216 to a base 3. Well, I can just express this as log 3 of 216 divided by log 3 of 6. And you know what, like if I was being asked to find the value, I could just calculate it as log 10 of 216 divided by log 10 of 6. So I could just type it into my calculator without those 3's as the base. Log of 300, remember that if you're not told what the log is, then it is 10. Okay, it's not 1, but it's 10. And so if I want to express this as log as a base 5, this would become log 5 of 300 divided by log 5 of whatever my my y value here, which in this case is going to be 10. All right, and with these last few questions, all you really need to do is, you can just input these into your calculator, and you should be able to solve it from here. So let's move on to lesson number 6. Lesson number 6, we were looking at the laws of logarithms. So we looked at a few other laws when we're working with exponents, but now we're working with, remember, we're working with the inverse of our exponential functions, so we're working with logarithms. The first law we were going to work with is the product law. So what's going to happen if I were to evaluate the following? Well, log 2 of 16 plus log 2 of 8, I can express these as my exponential functions, but I could also remember, I could go log 16 divided by log 2, and I get an answer of 4, plus log 8 divided by log 2. I'll get an answer of 3. So I get 4 plus 3, and that is equal to 7. All right, so let's continue. If I have log 2 of 16 times 8, this is the same thing as log 2 of 128. Now if I do the same thing in my calculator, log 128 divided by log 2, I'm going to get the exact same answer. I'm going to get that answer of 7. Alright, so let's look at the next one, log 3 of 27 plus log 3 of 3. Well, I'm going to use a shortcut, and this is going to be, well, I'm just going to type it in here again. I get 3 plus 1. So we're going to get 4. And the next one, this is the same thing as log 3, 27 times 3 is 81. And that is equal to 4. All right. So what are we actually looking for here then? Or 3 to the power 4, I guess could have done that. If we comment on both of these questions, if I compare A and B, they're the same answers, right? Number 1 and 2 have the same answers, and number 1 and 2 have the same answers again. And so using this later on, we're gonna develop our product laws and see what is actually happening here. Okay, so first let's look at our quotient law. So if I were to evaluate the following, 16 log 2 of 16 would be 2 to the power 4, so this would be 4. 2 to the power of 3 would be 8, so that's going to be minus 3. So 4 minus 3 is 1. Log 2 of 2, that's what this is equal to. 16 divided by 8 is going to give us log 2 of 2. Now 2 to the power of 1 is going to give us 2, so the answer there is 1. Log 3 of 27 minus log 3 of 3. Well, 3 to the power of 3 is equal to 27. 3 to the power of 1 is equal to 3. So I get 2. And I can rewrite this next one as log 3 of 9. And 3 squared is equal to 9. And so again, both answers are the same. Okay, so let's now look at the product and the quotient laws. So we just investigated what happens when if we were to add and then multiply, or subtract and then divide. So if I have log a of m times n, it's the same thing as saying log a to the m plus log a to the n. So if you notice that I could express this in either way. I can either add these as logs of the same base, or I can have one log and then I can multiply my arguments of m and n. And then so that's the product law. With the quotient law, I could, if I'm subtracting, then I'm subtracting my arguments with the same bases, or I could use one base and then divide my arguments, m divided by n. So let's look at how we would use these on these next two examples. So evaluate the following using the product law or the quotient law. So if I have log 2 of 12 minus log 2 of 3, remember we could express this as log 2 of 12 divided by 3, which would be the same thing as log 2 of 4. And if we were to switch this to exponential form, I know that 2 to the 2 would be my answer. So the answer to log 2 of 4 is going to be 2. All right, so let's look at this next one. I'm going to combine my product and my quotient law now. All right, so the first thing I need to do is if I have log 6 of 9 plus log 6 of 8, this can be expressed as log 6 of 9 times 8 minus log 6 of 2, which would be equal to log 6 of 9 times 8 is 72 minus log 6 of 2. Now my quotient law tells me that I can divide my arguments, so 72 divided by 2, which would be the same thing as saying log 6 times 72 divided by 2, or log 6 of 36, and that is also equal to 2. Okay, let's carry on. It's not a particularly long lesson, and I probably will not do all the examples, but I'll do enough for you to kind of get the hang of it. So the next thing we want to do is use the laws of logarithms. So we use our product law and our quotient law to write log x of 10 times log x of 75 minus log x of 2 plus log x of 3. And we want to write this as a single logarithm. Okay, so we're not actually being asked to solve it. We just want to write it as one logarithm. Okay, so just log x something. Okay, so the first thing we want to do is use our product law. Okay, so this is going to be our product law, and then we're going to have to use our product law in our brackets as well. And so since I'm subtracting both of these, I'm also going to have to use my quotient law, but we'll get there. We'll get there one step at a time. So to start off, if I have log x of 10 plus log x of 75, I can rewrite this as log x times 10 times 75, and then minus, if I have log x of 2 plus log x of 3, I can rewrite this as log x of 2 times 3. So this is going to give me log x of 750 minus log x 6. Now I can use my quotient law, and this is going to become log x 750 divided by 6, and that is equal to log x of 125. Now we want to evaluate this if x were equal to 5, and so this is going to become log 5 of 125. Well, 5 to the power of 3 is equal to 125, so my answer is 3. Okay, so you're going to do the exact same thing for the next question. And so to get you kind of started here, we're going to go log. So you're going to add these ones, which is your product log. And then you're going to divide these two, which is your quotient log, right? Because we're subtracting our logs. And then we're going to have to divide both these sides again to get your product, or to get your single logarithm. And then what you need to do is substitute your value of 2 into your expression. All right, down here what we need to do is the exact same thing we've been doing. So using our product laws, we want to put this into one expression, one log, and you should get an answer of G. And if you need help on this question, I will explain this one further in class. Now for class example number 5. Determine the value of 3 log 2p minus 3 log 2q if p divided by q is equal to 8. Okay, well, we're going to begin by just expressing this as a smaller equation. So 3 times log 2 of p. And what I did here was I'm going to divide the 3 out of both these equations. So it'll just be easier to work with because I'll be left with log 2 of q. So now this is going to equal, if I were to use the quotient law here, this will be 3 times log of 2. And that should be G. P divided by Q. And remember, P divided by Q, I'm told, is equal to 8. So this becomes 3 log 2 of 8. I know that 2 to the power of 3 is equal to 8. So this can become 3 times 3, and that is equal to 9. Okay, now let's look at the power law. Okay, so we looked at the product law, we looked at the quotient law. Now we want to look at another law, and that's the power law. So by writing 2 log x as log x plus log x, show that 2 log x is equal to log x squared. Alright, so if I'm starting out with 2 log x, and I know that 2 log x is going to be the same thing as log x plus log x. If I use the product law, then this is going to become log x times x, which is the same thing as log x times x is x squared. So now we want to prove that 3 log 2 of a is equal to log 2a cubed. Okay, well, if I have 3 log 2 of a, that's 3 times log 2 of a. That means that I have log 2 of a plus log 2 of a plus log 2 of a. All right, this would become, using the product law, this would become log 2 of a. If I multiply all my arguments, a times a times a, log 2a cubed. Now we want to write an expression equivalent to a log b of c. Well, if I were to rewrite this as an expression, just like I did over here, remember that this 3 became an exponent on my a, and so this a must become an exponent on my c if I follow the same logic. Log b of c to the power of a. So with the power law, it follows this rule. Log a of your argument m to the power of n is equal to n log a of n. So without using a calculator, we want to evaluate each of the following. Well, this is going to be, if I use this logic, then I know that n is going to become my coefficient in front of 12 log 4 of 16. Now, I know that 16 can be expressed as 4 squared. So I can break this down even further, so that's going to become log 4 of 4 squared. Now this becomes another exponent on my value of m. And so I can bring that 2 down. And I can do this as many times as I want, really. But this is going to become 12 times 2, if I bring that down, log 4 of 4. Now, this is not the only way to do this. We can use another method as well, but basically I can solve from here pretty easily, because this can become 12 times 2 times log 4 of 4 is just equal to 1. And so the answer is going to be 24. And we'll use the exact same process down here. Yeah, and then we want to simplify the following, and I think these are examples that you guys can handle on your own.